All right, I want to look at something seemingly a little different, but yet it turns out to be very similar to the estimating areas. I want to actually estimate distance traveled given some information about velocity. So I've got a table here where something has been moving and we've recorded some data about it. So the time here is 15 seconds. So at time zero, when this starts, apparently this object is moving at 5 feet per second. Right? 3 seconds later, the velocity is 6, so a little bit faster than it was before. By the time you're at the 6th second, you're moving at 7 feet per second. By the 9th second, it's slowed down to 4 feet per second. At the 12th second, it's slowed down to 2 feet per second. And by the end of 15 seconds, you're down to 1 feet per second. In that 15 seconds, can you approximate how far this object moved? Well, remember that distance equals rate times time. And if they had been traveling at the same speed the whole time, I would just say, hey, the speed was 6 feet per second, the time was 15 seconds, and I'd multiply them together to get 60 plus 30, 90 feet. But that's not the case. The speed is changing, or the velocity is changing. So I'm looking at this in smaller pieces. I'm saying, well, let's just look at it at 3-second intervals and do an estimate. All right. So for each little subinterval of 3 seconds, I'm going to either pick the left side or the right side as how fast I was going for that subinterval. So let's first of all look at the left endpoints. So my left approximation, for that first 3 seconds, I'm saying I'm traveling at 5 feet per second the whole time. So I've got rate times time, a rate of 5 feet per second times 3 seconds. Then in the next subinterval from 3 to 6, again, that's a time of 3 seconds. It's either 6 or 7, and I'm choosing the left side, so it's 6. So a rate of 6 times a time of 3 seconds. From 6 to 9, another 3 seconds, I'm going to say I'm traveling at 7 feet per second. So 7 times 7 times 3, right? And then for the next 3 seconds, I'm looking at 4 feet per second, and for the last 3 seconds, I'm looking at 2 feet per second. Right? So that left-hand endpoints looks like 15 plus 18 plus 21 plus 12 plus 6 for a grand total of 72. Yeah. Is that estimate too high or too low? I think it's kind of hard to say because the data is going from 5 to 6 to 7 to 4 to 2 to 1. So I think initially, for those first 3 seconds, I think I was underestimating and then underestimating and then probably overestimating and then overestimating and overestimating and overestimating. No, actually the last one I don't do that last one, right? I have 1, 2, 3, 4, 5 subintervals. 1, 2, 3, 4, 5, yeah. So actually I'm guessing I probably overestimated. It looks to me like there's a lot of overage here for the little bit of underage there is there. So I'm guessing it's probably less than 72. We could check with right-hand endpoints. So there's still, 5 subintervals that are all of length 3, so I'm saying times 3 here. But for this first one, rather than choosing the 5 to multiply by the 3 seconds, I'm going to choose the 6. And in the second one, rather than choosing the 6, I'm choosing the 7. And then instead of the 7, I'll choose the 4. And instead of the 4, I'll choose the 2. And instead of the 2, I'll choose the 1. So there's my same 5 intervals, but different heights because I'm looking at right-hand points instead of left-hand points. So this is now 18 plus 21 plus 12 plus 6 plus 3 for a grand total of 60. And again, for the same reason, I think that that first one was probably overestimating. I think this one is probably underestimating. And I'm guessing that we're somewhere in between. Now notice, this is, in a sense, it looks like an area here. But each one of these is a rate. It's a feet per second. And then I'm multiplying by seconds. So the result is feet. So this was 72 feet, or 60 feet. So from this information here, I'm thinking that this object moved somewhere between 60 and 72 feet in those 15 seconds. Okay. Notice, it's a very similar process to what we were doing with calculating volumes. Right? If I have that the velocity is some function of time, so let's say time is measured in seconds and the velocity is being given in feet per second, and maybe this is meters per second, or maybe this is hours going in and this is miles per hour going out, or kilometers per hour, or whatever. Time is going in, speed is coming out, velocity is coming out. And we've got some time interval that t is on the somewhere between a and b. Then we're calculating the distance. It's approximately equal to a summation, right? We're looking at a sum, I equals 1 to n, of, I need a velocity. So actually, a velocity times a bit of time. So I'm taking my t-axis here from A to B, and I'm, and I'm cutting it into a bunch of equal length intervals. Each length there, I'm going to call delta t. It's equal to b minus a over however many I'm chopping it into, n. For each subinterval, I'm picking a point and plugging it into my height function. Not my height function, really, my velocity function. So for this value of t, how fast am I going? That velocity times this bit of time, well, it kind of looks like a rectangle, and you're finding the area of the rectangle, but you're not doing inches times inches. You're doing seconds times feet per second, and that product is giving you distance. So a time interval of delta t and a velocity of whatever you get when you plug that t value in here, this t value in, get that velocity, multiply by the width there, and you've got distance. Are we calculating area? Kind of, because if you thought of this same function as giving you just a height for a distance over, then you'd be calculating the area under that. But when you're thinking of it as a velocity function, then what you're doing is you're calculating distance traveled in that amount of time. So there's various things, and we'll look at other examples too in the future, where it's the same idea of you're chopping up something and multiplying a little bit of length in one direction times the function value in the other direction. Sometimes it's area, sometimes it's distance, sometimes it'll be volume, sometimes it'll be something else. It's just a matter of what's the function giving you as an output and what's the variable representing as an input. This is a very, very common process, and we'll do it time and again here through Calculus 2.